Okay, thanks for agreeing to be on our advisory board. We just wanted to put together a quick presentation to give an overview of the project so that we can take advantage of the time when we're together to get your feedback. So here's an overview. We were motivated to do this project because we think online homework is one of the most used technologies in higher ed, and we think we can improve it in two major ways. One is to provide the right level of scaffolding for students and to help them be able to solve problems really from a blank page. So that's what we spend most of the time on, and that's what I'll mostly talk about. And we also have done less work, but I hope it's interesting, in support for argumentation in the context of intermolecular forces. So to help set up what we're in terms of providing scaffolding, here's two examples of interfaces that are common in online homework systems. This is a low scaffolding one. Basically gives the student a problem, asks them for the answer. It's good because if they succeed, it means they really can do this, but it's not ideal because if they don't know how to do it, there's very little support for them. So another approach is to provide very high scaffolding, but with the current tools that at least we have used and have had available to us, it's difficult to not sort of solve the problem for them while trying to get them, give them help along the way. It's like here's an interface that really asks for details, and by the time you know that these are the questions to ask, you've actually done a lot of the reasoning for them. What we're trying to do is create a system that has the advantages of both, and it combines a GUI that allows for open-ended input with a tutor engine that monitors what they're doing and provides hints and feedback as needed. There's also a tool for gathering log data on what the students are doing. So in the first year of the project, we focused on developing the tool and gathering information from students on how well that tool is working and how we can improve it. We started off by looking at paper-pencil solutions to the problems we were planning to support. We did a few rounds of editing the GUI and then think alouds with students, and we also did a focus group at Iowa State where students used the interface with TAs, and the TAs guided them through some discussion questions on to what extent the interface was working for supporting their problem solving. In this past year, so this is the end of the second year of the project, and it's a 3-year NSF grant, but we're expecting to extend it to allow us to do more gathering of data. The development will be rounding up at the end of the 3 years, but we want to extend it to be able to gather more information from classrooms. So we had two sets of materials that students used. One was limiting reagents, reaction stoichiometry, and that was used at Iowa State, about 100. It allowed us to test whether we can deliver an RCT, so we made treatment and control conditions, and we delivered them random assignment. It seemed to work fairly well, but there wasn't a difference in conditions. It wasn't a long enough statistical differences, so mostly just debug the system. It also allowed us to gather log files, and we're using those to understand how best to provide hints and feedback to students. For chemical equilibrium, CMU 150 at Iowa, this was a little bit different. The reaction stoichiometry one, we had hints and feedback in there. In chemical equilibrium, we only provided feedback on was your answer correct or incorrect, and there was very minimal hinting. And the idea there was we would gather data on what students do to solve the problem, and without interfering by guiding them in certain directions. And that was an attempt to gather enough data that as we create the hints and feedback, we can sort of make sure we're supporting all the things students might really do. So I'm going to move into talking about the GUI and modifications made to it as a result of this process. Here's what it looks like. We've got a student workspace, which starts out blank. This is showing them pretty much towards the end of solving a problem. Problem statement, controlled, oops, sorry about that. controlled vocabulary, and hints and feedback. So I'll go through some of these in more detail now. This is some of the artifacts we use to decide how students do things. You can notice there's mixes of writing a reaction and writing math. There's sometimes they decide to label, this person is very good about attaching labels to most numbers, but there's many different things you can say in those labels, like amount, the unit, the context, like is it produced or is it consumed. Here's someone much more sloppy, much less detail provided. And intermediate quantities by this person rarely have units or substances attached to them. And I think that's fine. I think many people, including experts, will not fully denote all of their quantities. And this sort of shows notations that we know are popular, but we don't really think it's important to sort of do the picket fence thing. So we decide not to support picket fence stuff. Elements of the GUI. One was just are we going to have them enter these mathematical expressions? There was an open source project, I think out of MIT, called Guppy that turned out to be a good base for this. There's lots of different things they might want to do with the equation, and eventually those ended up in this options menu that presents them with what they can do to modify this equation. We also allow students to attach labels. We attach here equation 1 as a default label that we generated, and students can modify that. We don't parse that though, so if there's some information that's there that's incorrect or correct, the tutor is not aware of it. We just have it there as a convenience for the students. We started by thinking of students typing in things like substances, labels, and units, and eventually decided that we had to use a controlled vocabulary for that. So we now have this menu they can click on, or they can use hotkeys to insert these values. Notice X for the unknown X in a quadratic equation is also in the controlled vocabulary, not just typed. ICE tables were common enough that we thought we should support those as a way of reasoning. And then to report answers, we decided to go with the claim style. So it's like make a claim. The first one here is one for limiting reagents, and this is one for final quantities. It's not really a very sophisticated claim, but at least it gets them used to the word claim, that they are making a claim and they are trying to justify it with things like this number is greater than that number. I'm going to shift gears into, from the GUI, it talks to this tutoring engine that has both working memory and production rules in it, and its goal is to sort of monitor student actions and provide hints and feedback when the student either asks for a hint or puts in an incorrect answer. So in terms of authoring, our goal is to be fairly flexible, that the tutoring rules, the production rules are general enough that you can author many different problems. And in many cases, like stoichiometry here, you would just need to say, here's the given quantities, and here's where I want the student to end up, and it knows how to connect from the givens to the target quantities and support students as they move along that pathway. And here's just an idea of how tutoring engines of this type work. We start with, say, the initial quantities here. They're in working memory. And we have some production rules that operate on those. And they work by every time the student enters something or there needs to be an update, you go through every production rule and see if the if conditions are met. If they're met, then you do some actions, and that could potentially put new things into working memory. So here's a more concrete example of that. We're using the cognitive tutor authoring tools from Ken Kadinger's group, co-PI on this project. There's a rule that's convert grams to moles, and working memory has an initial amount of copper oxide in grams, so that matches the if statement. It gets converted to moles, and that goes there. So this might not be a productive, in this case it is a productive step, but one issue is that the production rules will just run and generate valid things that can be done. here's examples of types of production rules. We start with some initial quantities and production rules for solving the problem in the correct way fire and put their numbers into working memory. We also have buggy paths so that common mistakes or misconceptions of students, in this case it's misidentifying the limiting reagent. If a student puts in a number like 2.1, that matches this fact in working memory, and so we now know this. Well, because the student hasn't attached units and quantities to it, we don't know for sure that they know what this number is, but we have the information that it may be the initial moles of copper oxide, and that might be what they're doing. We also, if they put in 6.30, we can flag that as likely this mistake that we can give them feedback on. In developing our rules, say for limiting reagents, we try to consider all the different ways a student might solve the problem, or that a teacher may teach their students how to solve the problem. We initially came up with these three strategies for limiting reagents, so which produces more product, and then reject the hypothesis that something is limiting if it produces more product than the other things. This one, we've got a of moles reaction, which is the way I like, because it sets them up for equilibrium, but I don't think very many teachers teach it this way. The moles of reactants versus the ratios of the stoichiometric coefficients. And through log files, just recently we discovered another strategy that Tom Holm pointing out to us has been in textbooks, used to be in textbooks a lot, and that's probably why we're running into it, but it has not been in recent textbooks, so it's probably fading away. And if we match one of these quantities, then we have an idea that they're probably following that strategy, and we can shift our hints and feedback to that strategy. There's also some subtlety in that these quantities may not be that distinct. So this quantity here might be the same as one of these quantities, and there is some ambiguity that we'll need to deal with. For supporting chemical reasoning, we built in the idea of hypotheses. So quantities, in addition to having a unit, a substance, and a context, they may also have a hypothesis attached, and these numbers are legitimate to calculate by students as they're going through and thinking through the problem. This is not an error, it's just an intermediate quantity based on this hypothesis. And then when they identify a limiting reagent, we can see or rejecting one of these hypotheses. The final component I'd like to talk about is the log of the student and tutor actions. So it looks like this. We get a very long file, and the cognitive tutor authoring tool CTAT has a system for generating this and monitoring it and pushing the files around. And we've been using them to identify what the student's doing and provide hints and feedback and see if the hints and feedback we're giving the student are good. It comes out a bit like an annotated transcript of what the student did. So here, all of these things that are labeled green, that means they match something in working memory. So they agree with something that we anticipated the student would do. And that was a correct thing. In some cases, it matches something we have in working memory that we think is incorrect. And then we also just have like untagged. So we can look through these quickly and see like what are all the student entries that we did not anticipate and figure out what the student might be doing. We also get to see the hint that the tutor generated, and is that the hint we would like to give if the student was at that stage in the problem solving. And that has really helped us figure out what's good and what's bad about the way we were doing hinting. What we'd like to build to is a learning curve analysis. What this shows is percent correct or assessment score, which is really did they make a mistake or did they ask for a hint, versus the opportunity to engage with that concept or idea. We would like to support things like converting grams to moles, identifying limiting reagents, justifying a limiting reagent claim. And we discovered that the way that we're saving the information now the tutor shop tools don't immediately are not immediately able to analyze those, but we're working on ways to change it so the tools work. The information is there, it's just not organized in a way that the current analysis algorithms work with. But I think we have that nearly fixed, and so we will be able to get learning curves for these interesting things. Right now, this is just a learning curve for how many times do they need to re-edit the equation they entered to get it right. So usually what this is saying is almost all the time students need to do just one or two revisions. Very rarely do they have to edit their equation 3 times to get it to be something that's a final equation. Hints are given when students ask for a hint. So the difference between feedback and hints is feedback is if something's wrong, like if they submitted some answer and it was incorrect, we would immediately give them feedback on that. Hints are by request of the student. And one style, and the style we have been using, is to write production rules that push hints onto a stack. Here's one that is kind of a strategy shifting approach to supporting limiting reagents, that if the student has not yet identified the limiting reagent, but they have calculated moles of each, we give them a hint on how to use what they've calculated to figure out the limiting reagent. If they have not yet calculated moles, we would give them a hint that they need to convert from grams to moles before they can go on to the next stages of the problem. Here's another style of hinting. This is at the stage where students have calculated the moles of both reactants. There's 2 different strategies here they might follow in order to identify the limiting reagent. And let's say that the last action the student took matched the moles of C. From this, we could figure out that the next thing they need to do is figure out the moles of C if B is limiting, and give them that hint. So this is looking for the next expert move and providing hint to the student to take that move. So there could be a trade-off in these 2 approaches. The production rules, I think, are in danger of being less general in that they assume a certain problem type. And so the production rules may support problems for solution, but that the hints wouldn't make sense. Even though the production rule system knows how to solve the problem, it doesn't know how to hint if we write hints in this way. But those hints might be able to better promote conceptual reasoning because they know more about the problem. Whereas the next expert move, this one is more general because the system can always find the next valid step, but it may be that the hint is less good at promoting learning because it'll just tell them what action to take and give them a hint on that action. It might be harder to build into that a context of why that's the right action to take. I'd like to move into like how are we delivering this content to students and what's our plan for the future in that direction. So CMU has this open learning initiative that we deliver course materials through, and so we have created modules in there that put these tutors in an overall context of instruction. We have an online course for chemistry that Sandy Razor is primarily responsible for, taking from the OpenStax textbook and putting it into the OLI system, making the examples sort of live pseudo-tutored examples and replacing the end of chapter problems with online quizzes. So it's meant to stand in as a textbook and homework system together. Looming is working with us to get that out to schools, and we have a couple community colleges in California that are currently using the system in addition to what we do here at CMU. And it's great because it gathers this coherent log file that has all their interactions with the learning materials and the tutors embedded in that overall context. But should we be considering other systems or avenues like WebAssign? Should we try and work with these other providers of online homework to expand our reach for these things? So that's one thing we'd like your feedback on. One of our goals is to just allow authors to easily create tutors for many, many different problem types. Some of the questions we're looking at there are, is it sufficient to just provide initial and target quantities when defining a problem? Do the production rules successfully go from initial to target and generate hints and feedback along the way that are useful? It's one evaluation question. How many different problems can we support? So right now we just have a few stoichiometry and equilibrium problems, and a short-term goal is to really expand that collection way out, and we'll discover along the way like what's the boundaries of problems we can support and not support. We do allow inputs like concentration versus grams versus other ways to report the quantities and ask for quantities to come out. Equilibrium, we're currently just doing single reaction equilibrium, but it allows intermediate K, so need to solve the quadratic, or making approximations that, say X is small because K is large or small. Thermochemistry, we have the rules, but we haven't tested them yet. And we'd like to extend this to acid, base, and precipitation chemistry. And I think we'll cover a pretty broad swath of the types of problems in introductory chemistry, including especially the problems that students most struggle with. So, as I said, we're going to try and develop a whole bunch of extra questions. We also want to work on, to what extent can we put the tutor inside other ways to provide hints and feedback to students. So OLI has many different tools for developing questions, and if for those parts of a problem that are not mathematical, can we couple multiple choice and other creative ways to get input from students to the CTAT tutors we're developing? An example of that would be if they generate data in our virtual lab, can we develop a tutor to help them, support them in analyzing that data? But we'd be interested in your feedback on content areas, problem types, things that are really being a barrier for students in these courses, and is there something we can do to help students with this? Another big focus of the coming year is going to be on ways to provide hints. So some ideas for additional ways to provide hints other than the ones I mentioned are top-level strategy hints that are authored at the time you write a problem. So in addition to saying here's the initial and the final quantities, you can provide some sort of top-level strategy hints to get students started at that problem. And we can figure out ways to deliver those at the appropriate times. Another one is there's this idea of pseudo-tutors, which are tutors that support only a single problem. But our production rule system is capable of generating a pseudo-tutor for a problem, and then authors can go through and just modify. That pseudo-tutor will have a full support for hints and feedback the way we currently deliver them. And if someone wants to go through and say, well, I'd rather provide this hint, because, very problem-specific style, they can do that in an efficient way using CTAT authoring tools. Another thing, we've talked a lot about how to support strategy, and one thing that's come to mind are multiple choice questions, or that sort of, or other styles of asking students, what's the strategy you should use? Well, we're interested in any thoughts people have on how to really build hints and feedback that will promote the kinds of high-level reasoning we want students to have in these courses. This is the other style of tutor that we're creating. This one is on sort of general reasoning where you provide evidence in a claim or claiming evidence. And we have an OLI module in which Sandy went through and created these questions and ways to report answers that really guide students in a specific direction in constructing these arguments. They always ask students to compare ionic, polar, and dispersive forces. The idea is they decide whether these push these quantities towards one direction or another, and when there's competition, like if dispersion says something should boil at higher boiling point, whereas polarity says it should boil at a lower, we want students to realize that because those two are in tension, they really can't make a definitive prediction, and you would need experimental data in order to decide whether which force was actually in control of the system, or is the more dominant influencing factor. But what we're trying to do is really in response to this issue, we perceive that students don't know how to write good arguments. Like on AP exams, students just write on for sentence after sentence without ever really making a specific claim and backing it up with evidence. So some things we want to look for is students who've used these question types, does it influence the way they write answers on exams to questions of this type? And does it transfer to other question types? So here's where we could use some feedback, especially is this a reasonable problem space for us to be working in? Are there things out there we should be aware of that maybe we're not using or that we're duplicating and just replicating work? What should we be watching for in student reasoning on this? And also, should we consider less restrictive systems? So we have ideas for like drag and drop sentence construction, even within the CTAT tutoring system where we could potentially provide better tutoring. Is that all worth it? Should we be moving in this direction? And then here's the final set of questions that we thought of to bring up, and we're interested in any feedback you can provide us. But input on the design of our learning studies. So we're looking at the log files. Are there things that we can do with these log files that help us better understand the transition from novice to expert? Are learning curves likely to help with that? Are there other things we should be looking for? Are we working at the right level of grain size for supporting student problem solving, or should we think of that out somehow? Is it worthwhile using some of our student population to do random control trials, or is it likely that we won't get the kind of information we really need at this stage of the project, and we should focus on more qualitative ways to gather data and analyze data? And any input you have on better ways to gather data and analyze data on student reasoning would be appreciated. So thank you very much for your time. I'm looking forward to talking with you on Wednesday.